Okay, let's dive right into this explainer. Today, we're unpacking one of the absolute most fascinating chapters in mathematics, probability. We're bridging that gap between simple games of chance and complex, real-world predictions. Seriously, we aren't just going to stare at dry numbers today. We're going to see how probability literally shapes our fundamental understanding of information itself. To guide us through the chapter, here's our roadmap. First, we'll hit the science of logic. Then, we'll unpack conditional probability, followed by multiplication and independent events. After that, we'll build up to total probability and Bayes' theorem. And finally, we'll wrap up by introducing random variables. Let's get to it. So part 1, the science of logic, and how we go about quantifying common sense. Let's start with a foundational shift in how we actually think about probability. Because, it's not just about rolling dice. It's a fundamental way of thinking. There's a quote by C.S. Peirce that brilliantly captures our core philosophy for this explainer. He said, "The theory of probabilities is simply the science of logic quantitatively treated." I just love that. We aren't just crunching abstract equations here. We're taking common sense, taking pure logic, and giving it a mathematical backbone. When we calculate odds, we are essentially mapping out the logical boundaries of our universe and, think about it, putting a strict, measurable value on our own uncertainty. Moving right along to Section 2, Understanding Conditional Probability, or what I like to call the shrinking sample space. This is where things start to get really, really practical. Before we throw any formulas at you, let's translate the math into plain, everyday English. Conditional probability is basically just asking, how does new information change our odds? Imagine you're trying to figure out the chances of event E happening, right? But then someone whispers in your ear that event F has definitely, 100% already occurred. How does that new piece of the puzzle fundamentally shift our entire perspective? Well, looking at the math, the probability of E given F relies on the intersection of both events. But honestly, the crucial takeaway here isn't just memorizing the formula. It's the concept that by knowing F has occurred, our entire universe of possibilities, what we call the sample space, literally shrinks. It goes from the original massive set down to just F. We are now exclusively operating in a world where F is true. Let's ground this with a concrete example straight from the chapter. Say we toss 3 fair coins. Normally, we're looking at 8 possible outcomes, right? But what if we know event F has already occurred, meaning the first coin is absolutely a tail? Boom, that instantly eliminates half of our original possibilities. Our sample space shrinks from 8 outcomes down to a very manageable 4. Now, let's pause and look within this new, tiny universe of 4 outcomes. We're hunting for event E, getting at least 2 heads. Scanning those 4, there's only one outcome that actually fits the bill. Tail, head, head. So our conditional probability is simply 1 out of 4. See how beautifully logical that is? Which naturally leads us to ask a pretty vital question. Does event F always impact event E? Like, does knowing this new information mathematically guarantee a shift in the odds? Or are there times when new info is just completely useless to us? That brings us to Section 3, Multiplication and Independent Events, examining when events actually connect. To answer our question, we've got to look at how probabilities multiply when multiple things happen together. Enter the multiplication rule. If events actually depend on each other, the probability of both E and F happening together is just the probability of the first event, E, multiplied by the conditional probability of the second event, F, given that E has already happened. It's like a chain reaction of logic, really, and it's the absolute essential engine for these complex calculations. Now, look at the contrast here. It's pretty striking. If the events are dependent, we have to use that conditional probability we just talked about. But if the events are entirely independent, meaning one happening tells us absolutely zilch about the other, that complex conditional piece just vanishes. The formula beautifully simplifies. The probability of E and F becomes just the probability of E times the standard probability of F. Simple as that. Think about drawing a single card from a standard deck. Let's say event E is drawing a spade, and event F is drawing an ace. Does knowing the card is an ace change the likelihood that it's a spade? Nope, not at all. A quarter of the deck are spades, and exactly a quarter of the aces are spades. Whether a card is a spade has absolutely no mathematical impact on whether it's an ace. They are completely oblivious to each other, perfectly independent. All right, moving into Section 4, Total Probability and Bayes. This is about working backwards. And honestly, it's the climax of the mathematical scaffolding we've been building today. But before we can look backward, we have to grasp the whole picture using the theorem of total probability. Imagine a sample space partitioned into several completely different mutually exclusive paths. It's like having different roads that all lead to the exact same destination. To figure out the total chance of arriving, you can't just look at one single road. You have to sum up the probabilities of traveling down each individual path, weighted by the chance of making it to the end of that specific route. And that brings us to the crown jewel of probability theory. Bayes' theorem flips the logic of total probability totally on its head. Instead of predicting the future, it lets us look at an outcome that has already happened and mathematically calculate the probability of the specific cause that got us there. It's literally mathematical detective work. It is the ultimate tool for updating our beliefs based on new evidence. Fun fact, this is actually the foundational logic behind modern machine learning and, well, how our own brains update beliefs. Let's ground this with a classic, super practical example from the chapter. Imagine a doctor arriving to see a patient. We have his prior probability of taking different types of transport, train, bus, scooter, or other. Then we have the conditional probability of him being late given that specific transport method. So, for instance, if he takes the train, he has a 1 in 4 chance of being late. Take a quick second to think about how these different roads map out his chances of arriving on time. Now, here is where Bayes' theorem works its absolute magic. Step 1. The doctor arrives, and guess what? He's late. That is our known outcome. We are now working entirely backward. Step 2. We calculate the total probability of him being late across all those different vehicles. Step 3. We take just the train is late path and divide it by that total late probability. And the math works out perfectly so that the train accounts for exactly half of the total late risk. So, by crunching these numbers, Bayes' theorem reveals there's exactly a 1 in 2 or a 50% chance that the train was the culprit for his tardiness today. We observed the effect and mathematically deduced the cause. Mind-blowing, right? Let's wrap things up with Section 5, introducing random variables and mapping the space. This is going to set the stage for our next big mathematical leap. Up until now, we've been dealing with events described in words, right? Things like getting 2 heads or drawing a spade. But to do real advanced mathematics, we need numbers. A random variable isn't just some unknown x from your high school algebra class. It's actually a specific rule, a function that assigns a real, tangible number to every single possible outcome of an experiment. It completely demystifies the abstract. Here's a perfectly simple way to map it. If we toss a coin twice, our sample space is heads heads, heads tails, tails heads, and tails tails. Now, if we define our random variable x to simply represent the number of heads, we can easily map this abstract, word-based sample space into clean, totally usable integers, 2, 1, 1, and 0. Just like that, we've translated physical reality into pure mathematical data. And that translation leaves us with a totally fascinating question to ponder. Once we convert all possible outcomes into clean numbers using random variables, what overarching shapes and patterns will these complete probability distributions reveal about our world? We've honestly only just scratched the surface of logic quantitatively treated. Thanks so much for joining me on this explainer of the chapter, and hey, keep questioning the probabilities around you.